The last section of Chapter 5 deals with the quantum mechanical model and where the model came from. The quantum mechanical model actually grew out of the study of light. Now, light consists of waves. So light moves in a wave-like fashion like this. We're going to define a few terms. Amplitude is the height of the wave. So amplitude would be from the top to the midpoint. That's your amplitude. That's a distance. Lambda is the distance between crests. That's the top. So here's your lambda, and it kind of looks like an upside-down Y. So as long as you go through one complete cycle, that would be a wavelength. I could also measure from bottom to bottom, and that would be the same distance, that lambda. Frequency, the third term, is designated with nu, and nu kind of looks like an upside-down horseshoe, and this is the number of wave cycles that pass a point per given time, usually per second. So frequency is I'm counting the waves that pass a specific point per second. Light consists of electromagnetic radiation, and here are a few types of electromagnetic radiation. You have radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Radio waves, this is the low energy end of the electromagnetic spectrum. Gamma rays is the high energy end of the electromagnetic spectrum. And obviously the only portion of the electromagnetic spectrum that we can see is visible light, and visible light goes from red to violet. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. That's the only portion of the electromagnetic spectrum that we can see. We're going to use two equations here when we look at light and doing these light equations. The first one is C equals lambda nu. So in this equation you have wavelength right here, and you have frequency right here. And c is a constant. C is the speed of light. So c is always 3 times 10 to the 8th meters per second. And the second equation we're going to use relates energy, which is the E, to frequency again. So frequency is in both equations. And h is a constant. H is Planck's constant, but it is always 6.626 times 10 to the negative 34th joules times seconds. Those are the two equations we're going to use, and these relate wavelength to frequency to energy of light. So let me go through a couple examples. The first one, I have frequency. So I have this symbol. I want to find wavelength. Well, wavelength is this. Go back to the two equations that we have. The one that relates wavelength to frequency is this one right here. Now I want to solve for wavelength. So I want to solve for this. Rearrange that equation. You get c divided by frequency. Just some algebra there. C is the speed of light. Speed of light doesn't change. It's always 3 times 10 to the 8th meters per second. We're going to divide by the frequency. The frequency is given in the problem. Now hertz is the same thing as saying 1 over s. So hertz, 1 over s, s to the minus 1, they all mean the same thing. But you'll see that your seconds will cancel out. You're going to get a wavelength in meters. So the wavelength of this radiation, of this light, 2 times 10 to the negative 5. Go through the next one here. What is the energy of a radiation? So we want to find E, and we're given wavelength. We're given wavelength, 500 nanometers. I want to find energy, which is E. Well, here's the thing. If you're given wavelength in nanometers, you always convert nanometers back to meters. So the units will cancel. So nano is 10 to the negative 9. That's the first thing I'm going to do, is convert my wavelength back to meters. There's my wavelength. It's now in meters. I want to find energy. In order to find energy, I have to know frequency. So here's what I'm going to do first. I'm going to find frequency. If I know wavelength, I can use this equation right here. Frequency is the horseshoe. That's the nu. I'm going to take c, which is the speed of light, going to divide by the wavelength, and I changed the units to meters already. 5 times 10 to the negative 7th meters. Because you see here it's 3 times 10 to the 8th meters. The meters have to cancel out, so I couldn't have used nanometers. I'm going to get my frequency when I divide, and the frequency is going to be in 1 over S. Or you could also say hertz. But those are the units for frequency, 1 over S or hertz. And if I want to find energy, H times nu, H times frequency. So I had to use both equations here. H is the 6.626 times 10 to the negative 34th joules times seconds. Frequency I just found. Your seconds cancel. We're going to get energy of this particular light in joules. .98 times 10 to the negative 19th joules. That's the energy of 1 photon of this radiation. So how does light come about? Well, as atoms absorb energy, electrons move to higher energy levels. So electrons do not always stay in the ground state. They move to higher energy levels. But they don't like to be in the high energy levels. They like to be close to the nucleus. So they lose the energy by emitting light as they return to lower energy levels, or the ground state. And we've been doing ground state electron configurations. They do not always stay in the ground state. Electrons can move to higher levels in the excited state. Ordinary light is a mixture of all wavelengths of light, but the light emitted by atoms consists of specific wavelengths or specific colors, because a specific wavelength has a specific color associated with it. When the light from atoms is passed through a prism, it separates into discrete lines to give the atomic emission spectrum of that element, and no two elements have the same atomic emission spectrum. And I will show you examples of some atomic emission spectra in class. And we'll look at different elements, and you'll see that no element is the same. And so we'll kind of look through these. We'll look at some spectra in class. So the ground state is the lowest possible energy. That's what we've been doing. We've been doing ground state electron configurations for atoms. For example, hydrogen's ground state is N equals 1 because hydrogen's electron configuration is 1s1. But the electron doesn't always stay in the 1s orbital. It moves to higher levels. So excitation raises it to N equals 2, 3, or whatever. It doesn't like to be in the higher excited state, so as that electron comes back down, light is emitted. But light is only emitted when an electron drops back to a lower energy level. So let me kind of draw a picture here. And I'm going to use the Bohr model to kind of explain this. But remember, we know that electrons do not orbit the nucleus. But the Bohr model just makes the explanation just a little bit easier when we think about how light is produced. So I'm just going to draw a few electrons here. And we're just going to say there, this is N equals 1, close to the nucleus. This is N equals 2, that's further. N equals 3, gets further from the nucleus, and so forth. Well, electrons are in the ground state. As they absorb energy, whether it's through heat or electricity or whatever other means, they move to higher levels. So they're going to move to higher levels. Well, they don't like to be in these excited states. So once they get up to this high level, they want to come back down to the ground state. And as they come back down to the ground state, they emit light. So this is how light is produced. Electrons absorb energy, move to higher levels. As they come back down, they emit light. They want to be in the ground state, but atoms are continuously absorbing energy from different sources. And that's what moves them to the higher levels. They come back down, they emit light. Electrons can jump 1 energy level, they can jump 5 energy levels, they can jump 10 energy levels. Depending on how many energy levels they come back down, that determines what light is produced. Different energies of electrons jumping corresponds to different wavelengths. And different wavelengths mean different colors of light, if we can see them, or different types of light, whether it be ultraviolet, infrared, visible. So the different energies that those electrons jump or come back down correspond to different wavelengths, which correspond to different types of light, whether it's visible, ultraviolet, microwave, whatever. So a quantum of energy is related to the frequency by the equation E equals h nu, where E is energy, nu is frequency. The light emitted has a frequency directly proportional to the energy change. And in this equation right here, there is a direct proportionality between energy and frequency. For the atomic spectrum of hydrogen, hydrogen was studied extensively because hydrogen has one electron. So it's very easy to study hydrogen. There are 3 series: the Lyman, the Balmer, and the Paschen series, and these all correspond to where the electron ends up. If the electron goes from an excited state to n equals 1, it doesn't matter if the excited state was n equals 5, n equals 10, n equals 7. As long as it lands on n equals 1, it produces ultraviolet light. As long as it goes from an excited to n equals 2, it's visible, and excited to n equals 3 is infrared, regardless of where it starts. Albert Einstein proposed that light could be described as quanta of energy, which he called photons, which behave as particles. So we have the wave nature of light. Light acts as waves. But Einstein also proposed that light can behave as particles, which he called photons. And this leads us to the dual wave particle behavior of light. De Broglie said that all moving particles of matter can behave as waves. So de Broglie says that when I throw a baseball, the baseball moves in a wave-like fashion. And this has been shown to be true, but we're unable to see the wave-like motion of the baseball because the mass must be very small. The baseball's mass is too large. So de Broglie's hypothesis has been shown to be true. Everything moves in a wave-like fashion. We're just unable to see that. So baseballs move in wave-like fashions. We move in wave-like fashions. Cars move in wave-like fashions, but we're just unable to see the wave-like motion because the mass must be very small. 2 terms down here: classical mechanics, quantum mechanics. We're dealing with quantum mechanics, motion of subatomic particles and atoms. Right now we're looking at electrons. Classical mechanics describes the motions of baseballs, cars, people, stuff like that. Those are just 2 definitions. Everything we've done with the quantum mechanical model is based on the Heisenberg uncertainty principle, which says it is impossible to know exactly the velocity and position of an electron at the same time. Because when you try to measure the position of an electron, it changes velocity. So everything we've done with the quantum mechanical model, which is basically electrons move randomly, is based on the Heisenberg uncertainty principle, because we do not know the velocity and the position of an electron simultaneously.